Okay, guys. In this video lesson, what we're going to do is talk about voltaic cells. Okay. Another word for voltaic cells is a gravimetric cell. And what voltaic cells are for us is basically they're the building blocks of batteries. Okay. So when we started this unit, we talked a lot about redox and oxidation reduction and what is gaining electrons and what is losing electrons. Now, the reason why we start the unit with that stuff is because that's the foundation, or that's the foundational chemistry behind how batteries work or how voltaic cells work. So we first have to understand what is gaining electrons, what is losing electrons, for us to be able to understand how can we take these movement of electrons, gaining and losing, and actually create current or create a flow of electricity across a circuit, a light bulb, a battery, a cell phone, or whatever it is. So how do we use chemical energy to power our devices? Okay. So here's our first step into that process now that we know redox is how do we actually get current to flow? And we use that by using voltaic cells. So we're going to watch the little video here. And then once we're done the video, we're going to go into a couple of applets to kind of look at a little bit more detail. And we'll go from there.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
Okay, so that's kind of the overview. Now let's break it down in a little bit more detail for us, okay? So we're going to go to this first little applet here to start off. Okay, so as this thing loads up, we kind of see what's kind of going on here with our circuit. Here's a simplified drawing of it. I think this is kind of a nice one for us just to use to kind of take a look at what's going on. And it shows a couple of visuals. First of all, how do the electrons flow? Okay, so we have different parts of our voltaic cell. We need to make sure that we understand what the anode is. Okay, so our left-hand side here is our anode. That's our negative side. So an or anti is negative. And then we have our positive side, which is our cathode. Okay, what that tells us is that the electrons leave from here. They cross whatever we are trying to light up, whether it be a light bulb, whether it be a voltmeter that reads the voltage, whether it be power to your cell phone. This is where the electrons flow here and power something, and they go back into the cathode. Okay. Now you'll notice that on the anode, our zinc looks like it's something been biting it and chewing at it. That's because as everything runs, we actually lose zinc solid. It goes away, and we actually gain, if you look over here, copper solid. So let's take a look at what's actually going on real closely at our anode. Okay, so in this case we have zinc 2+ in solution, and over here we have copper 2+ in solution on this side. So let's take a zoom in feature here. Now in this scenario, we notice that the zinc metal, okay, is releasing 2 electrons, and it's leaving as zinc 2 plus. So we have zinc solid that's actually turning into zinc into solution, and it's leaving or reducing to 2 electrons. Okay, so here we have zinc becoming a 2 plus. So zinc is actually losing electrons here. Okay, we lost a whole chunk there. Zinc is losing electrons, so this is our oxidation side of our reaction. Okay, so at the anode we have oxidation. So that's something you probably want to write down. Okay, so the anode is where oxidation occurs. Okay, so it is losing electrons here because they're being lost and they're coming down the wire. So then at the cathode, we should be gaining electrons for the copper, okay? So in this case, we have copper ions, and they bump into this copper plate that has these extra electrons. So these coppers are gaining 2 electrons, and as they gain electrons, they get reduced, right? Gaining electrons is reduced. Leo goes Gur. So what happens is over time, we actually are building more copper to our cathode over here, which is gaining these electrons, and we are getting more copper on here. So on this side of the Voltaic cell, we have reduction. Copper ions gain 2 electrons to become solid. Okay, so we have oxidation going on over here. We have reduction going on over here, and that's kind of how the electrons flow. We're essentially creating the same thing as a redox reaction, but we're just separating it by a wire. So we're forcing the redox reaction to travel through a wire, which then we can use the energy of these electrons to power our device or to create voltage. Okay. Now, one thing that's very important to this, to make the whole thing work, is the salt bridge. Okay. Without the salt bridge, there wouldn't be a connection between these 2 vessels, and without that connection, we can't get electricity to flow. Okay. So let's take a look at what the salt bridge is doing for us. Now, the salt bridge has a really simple job. It provides charge balance. So inside this particular salt bridge, we have potassium ions and chloride ions. And what's going on is that the potassium ions and chloride ions, they're both going to be spectators in the actual chemistry. However, we need to have a balance of charge. If you imagine, as the zinc here breaks down, so as we start to get zinc ions into solution, more and more zinc ions coming in solution, so as this side here would become more and more positively charged. So this actual container would become heavily positively charged over time. This container, as we lose these ions and they become solid, okay, we lose positive charge. So on this side, the sulfate wouldn't leave, but we would be losing all our Cu2+. So this side would become heavily negatively charged. So if you have a positive side and a negative side, eventually that would shift the equilibrium, and as a result, because we are gaining on this side and losing on this side, if there was no connection between the 2, it would stop the current flow. Okay, so it would not run. What this does is you move electricity. So on this side, since we are losing electrons and we're gaining positive over here, the chloride will run in this direction. So we'll take a look. You'll see that the chlorine is going to run the negative right here, the negatives. They're going to run to the left. So they're going to replace negative ions on this side to balance out the extra positive ions we get over here. On this side, we're going to add potassium, so it's going to balance out the extra negative ions we have over here. Okay, so the salt bridge provides charge balance, or make sure that everything is balanced out in terms of charges, so everything continues to react chemically. Okay, so it's there to basically stop the Chatelier's principle from controlling this process. Okay, so that's our first animation. If we go back to our slideshow, the second one here, I like it because what we can do with this one is we can actually modify the cell a little bit. So here we have a voltmeter, and we can choose what we have. So I want to choose some different metals. Okay, so I'm going to use, we've seen copper and zinc, so let's use silver. Okay, so I want to put silver metal in this side, which means the solution I want to use that is going to be silver with something. So these are all nitrates. Again, good spectator. So we have silver nitrate solution in this side. Over here I can't use silver again, so I can use copper or zinc or a hydrogen electrode. We're going to ignore hydrogen and just going to use copper or zinc. Okay, it doesn't matter which one we use, you just can't use silver. So let's just say we're going to use copper. Okay, so we put copper in this side, which means our solution has to be the copper-based solution, so we have copper nitrate solution. Okay, as soon as I flip the switch on, we should see current flowing. Now we don't really know which way it's going to flow because we don't know if silver has a bigger reduction potential than copper, or copper has a bigger one. So we don't know which way the current's going to flow until we flip our switch. So in this case, what we see happening is we see electrons flowing away from the copper and going this direction into the silver, okay? Which means the electrons are leaving here, so this is losing electrons, so we're being oxidized over here. Here we are gaining electrons, so we're being reduced, okay? So on this side, since we're gaining electrons, that's our cathode. On this side, since we're losing electrons, that is our anode, okay? If we were to flip the scenario where we turn our switch off, and let's say we put copper on this side, and we put silver on this side, and then we turn this thing on, okay? Now we can get electricity to flow in the other direction. So notice how now it's a negative voltage instead of a positive voltage, and now this becomes, we're losing electrons, so we're being oxidized. So this is our anode. Here we're gaining electrons, so this is being our cathode, or being reduced, okay? So depending on where we put the metals, in which side, we can get electricity to flow in any direction we really want to have happen. Okay, so depending on how you build your battery, you can actually force electricity to flow one way across the circuit or a different way across that circuit to provide power where you want it to go. Okay, so same idea, same setup. Here we just have a couple of different metals. Now if I flop out my metal, turn my switch off again. If I change my metals, let's say I use zinc now with silver instead, and I get my silver nitrate solution and my zinc nitrate solution, and I turn this thing on. Okay, notice how our voltage now is 1.56. Before it was 0.45. Okay, so there's a mathematical way to calculate what this voltage is going to be, and we'll learn that here in a day or two. But depending on which metals we use, we can actually change how much current flows or how much voltage we get. So the different metals like nickel metal hydride or lithium ion or cadmium batteries or alkaline batteries, all those different type of batteries have the ability to create different types of voltage or different types of current flow. And it's by using different metals or different combinations of substances within inside them. Okay? All right, so that's your basics behind a voltaic cell. This video down here is by a guy named Tyler DeWitt. It's about a 25-minute long video that he walks through what a voltaic cell is extremely slowly, giving you every piece, every part, and how they all work. I put it here not because I'm going to force you to watch it, but if this is kind of confusing to you and you want to watch a really good, slower version of what we just did, this is the place to go. Okay, so type this guy in, and that would be a good idea for you guys. All right, so here's our basic voltaic cell in our notes. Okay. Again, I'm going to go pretty quick through these slides. I'm going to go back here because these are ones that we've already talked about everything. We're just going to kind of review quickly for you guys. All right. So voltaic cell, oxidation occurs at our anode over here. Reduction occurs at the cathode. We see our two different half reactions down here. We see the movement of electrons this way, charge balancing with our salt bridge. Okay. Reminders at the anode. What is special about the anode? Okay. Electrons leave the anode, flow through the wire to the cathode. Okay. The electrons, as they leave, the cations go here and they dissolve into ions. In our cathode, we have electrons are coming to them, so as a result, the ions actually attach and become solid. And then that's our cathode side. Okay. Don't forget about our salt bridge. So the salt bridge is, even though it's a lot of spectators, it is a key piece of our circuit here to make this work. Usually it's a U-shaped tube or some sort of porous tube that allows us to keep charge balance. So you're going to have the negative flow going towards your anode, and you have your positive flow going towards your cathode, because it's going to be opposite of what the electrons are doing. So the electrons, which are negative, are going to come to the cathode and leave the anode. These work in the opposite direction to maintain charge balance. Okay. All right, that is it. Once we get this kind of figured out, the next step is to actually put numbers to this and talk about how much force, basically how much voltage we can actually generate by using voltaic cells. All right, guys.